Now we're going to be applying some similar, equation ideas for parallel metal plates, just like in the last Super Cram video for point charges. So in this case, I do have, parallel plates that I want to connect with the battery here. So let me just draw lines here to connect them to each other. So it should go pretty quickly here, just like that. And we'll just go ahead and continue to collect them all there and place them together, just like that. And let's remind ourselves what a battery looks like. The long stick is the positive charge in it, and the small stick is a negative charge. So that means this will be positively charged here, and this will be negatively charged. Okay, so, what equations apply here? Well, very similar to before. If I put a positive test charge here, okay, in, we will then see that the positive test charge will be, pushed away and attracted this way. So this plate will pull it away. This one will attract it. But what's unique about these metal plates is the electric field in between the two plates is constant. Okay, so what equation is useful is the VET equation. Volts is equal to ED. Okay, now really what this means is the change in voltage as it goes across is equal to a product of the distance between the plates and the constant electric field between them. So if we have 6 volts here, this plate has a positive 6 volts. Over here we have approximately 0 volts as the electrons are making or as the charges are making their way across. Okay, so if a positive test charge goes the entire distance, it would have gone 6 volts across. What if it only goes to about this location here? Well, this location here would be 3 volts. Why? Because our distance is only half the distance. Okay, so we have 6 volts here, we have 3 volts here, we have 0 volts here. About here would be 4 volts, 5 volts. So the voltage is dropping as we go across. Okay, so we start from high potential and then go to low potential. Now what if I wanted to find the change in potential energy as a proton goes across our plates? Okay, well, we can use the same equation. Q times V is going to equal electric potential energy. Okay, so, well, please remember that Q is a constant. It really means times the change in volts is equal to the change in electric potential energy. Okay, so if I'm going 6 volts across, whatever the value of my charge is, I just multiply that. Remember that volts does equal joule per coulomb. So if I've got 1 proton going across, I will multiply this by 1.6 times 10 to the minus 19 coulombs, and that would be how many joules I have. So whatever the value of the charge is going across, multiply that by my change in voltage, and that'll be my electric potential energy. So, it's really this equation here. My electric potential energy change is equal to my kinetic energy change. So if I'm starting here, I've got a lot of electric potential. I let it slide across. Okay, the change in electric potential is just a gain in kinetic energy. It'll have a certain value of kinetic energy just before it hits the plate over here. Okay, very similar to like mgh equals 1 FME squared in gravitational potential. So my gravitational potential converts itself into kinetic. Now if I'm going the other direction, I will then see a voltage rise, not a voltage drop. Therefore, I will have a gain in electric potential energy going this way. So I'll have to do work done. So if it goes across here in this direction, again, this is really work done. Again, my work is equal to negative if I'm going this way. If I'm going in this direction, my work is equal to positive. So one more time, please equate work done equaling the change in electric potential energy. This way I actually have to do work to the system. I'm giving electric potential energy to it, and if I let it go, it kind of falls back down pretty quickly. And again, just like gravitational potential, if I'm going upwards, I'm putting work into something as I rise it up. If I just let it fall back down, my change in gravitational potential energy is going to be negative as it converts to kinetic. Okay, so all very, very, very similar to that situation. Now what about the Robert Millikan experiment? Well, we have 2 parallel plates here, of course, and we will know the distance here. So we know the VET equation does work. So we really have a variable Okay, voltage source. Anytime we have a variable, we just draw an arrow across it. So that's our voltage source. So remember, he sprayed oil droplets on top. Okay, they would fall through a hole. A negative charge would develop on the oil droplet. And he would change voltage until the oil drop actually got suspended there. So what he means by that is force gravity downwards must equal force electric. Now remember, he did this by putting a grid in the background, and he could measure the size of the oil droplet. And using the density and the size, he was able to figure out what force of gravity was on it, because he could then calculate the mass of the oil droplet. So we know if it's suspended, that force of gravity does equal the force electric. Okay, so force electric is just equal to mg then. Okay, we can know the volts, we know the distance, you can then solve for electric field. So electric field is going to equal volts, okay, divided by the distance between the plates. Now, how did he calculate charge? Well, electric field is force electric per charge. So it's a force electric divided by charge. So electric field, we solve there and place it there. Force electric gets solved there, gets placed there. And then Q is electric field times force electric. Okay, and if you want to find out how many extra electrons are actually on that, take the value of Q that you just found and divide that by 1.6 times 10 to the minus 19 coulombs. And that'll tell you how many extra electrons are on that charge. And that's how the Robert Milken experiment works.